let's get back to this work time scheduling principle. And the principle essentially says that don't worry about the size of machine that you need. You take whatever is suitable for your algorithm, for your problem, and figure out how many steps it's going to take. A machine with that many processors, how many steps it's going to take. Okay. Once you have designed the algorithm at that level, at an arbitrarily large number of processors, then let an automatic scheduler schedule one, so for each step, schedule the work that was done at each step into P sections and allocate it among P processors. Let them do their share of that step and then go on to the next step. So you don't even have to worry about how to solve this problem on a P processor machine. You worry about solving this problem on however many processors you think naturally fits the problem. And then some compiler type jugglery will give you the algorithm for a P processor machine. All right. So now the total work done for your original algorithm is going to become important. And this is what we saw the last time also. So now you're counting the steps done by each processor at each time step. Okay, so Wi is the number of steps taken by each processor or processor I at a given time step. You take the sum of the number of steps taken by all the processors, take its ceiling, add it up. That's the total amount of work done, right? And we already saw that that is going to be just the total work divided by the number of actual processors you had plus the number of steps that your original algorithm took. Okay, you cannot change the number. You cannot go below the number of steps your original algorithm took, because this automatic scheduler is doing what? Taking each step and breaking it into as many pieces as it needs to. So the minimum number of pieces it can break it into is 1. There's at least n steps. Okay. So work done divided by P plus the original number of steps is going to be important, right? Because that's how many steps it is going to take on your machine, the one that had P processors. And so Tn is not unimportant. Okay. Cost, if you remember, was simply the number of steps multiplied by the processors, number of processors you used. So cost is the time taken by your parallel algorithm multiplied by the number of processors you had. So cost is going to be more than work, right?
Work is the number of cycles each processor was active for.
Yeah. So work is the sum of the cycles. And cost doesn't matter whether you are idle on a given step or not. I'm still going to count you for every step that I ultimately ended up taking. Okay. So we can clearly see that work is going to be less than equal to cost. And so if somebody says it is work optimal, it means that it's doing work which is equal to the sequential algorithm's work. Okay. And we are talking about, again, absolute optimality. If somebody says it's cost optimal, they're saying that the cost is equal to the number of steps that the sequential algorithm would have taken. Right? So if the cost, so if you think back of these example we were looking at last class, summation, how many steps did we end up taking? Log n, right? And the number of processors we used was order n. So the cost was n log n, in spite of the fact that the work was going down. It was n plus n by 2 plus n by 4. So work was only order n. The cost was n log n. Right? So work was optimal, cost was not. If its cost were also optimal, it would definitely be also work optimal. Right? So if I design a cost optimal algorithm, then I'm done. It's always going to beat any other algorithm on any machine. And so there is this Brent's theorem that is based essentially on, we'll look at this theorem in a slightly different way also. But it is, so look at that Wn over P plus Tn is the total time taken, right? So it says if I had P processors, now I've added the subscript P to signify that this is now the time with P processors. T sub P of n is what we had on the last slide, right? Work done divided by P, work done of the original algorithm divided by P, plus the time taken by the original algorithm. You would want those two to be as balanced as possible, right? So the Brent's algorithm says, or Brent's theorem says, that you would want Wn over P and Tn to become equal. Then your order is going to be the smallest. Right? Otherwise, your order is driven by whoever is the bigger. Tn is bigger, then it's order Tn. Wn over P is bigger, then it's Wn over P. So if you want to make sure that neither of them is bigger, you bring them to the same level, asymptotically. Okay. And so you say Wn plus Pn, P times Tn, should be order Wn. If that is the case, then P should be order Wn over Tn. Question?
The optimal number of processes.
That will be the optimal number of processes. Right? So now let's look at this optimal, the summation again, but this time we're going to make it cost optimal. Reminder, work was order n, cost was n log n. But now we do the same thing, but doing everything in parallel all the time, you have to make a few things sequential. We're going to start with an algorithm that says you've got not n processors, but n over log n processors. Okay. Now you're going to add the n things using the n over log n processors. So what's an algorithm? You take n by log n of them. Each processor takes its share, equal share, fair share. It adds them up together. How much time did it take? Each one had log n, right? N by log n processors distributing n things, each gets log n. In log n time, you are able to do your sum, local sum. Now I'm going to do the same thing I did before, because I've got these n by log n partial sums, and I need to add it together. I'm going to assume n by log n processors for this part. Again, right? That's what I had assumed for the first part also. How well would n by log n processor do? N by log n processors, n by log n things, same as before, right? The total number of steps will be log of n over log n, which is same as order log n. Total number of steps in the second half is also log n. Total number of steps in the first half was also log n. Total number of steps has remained log n. Okay. What about the cost? N by log n processors, log n steps, cost is the product. Right? So cost now becomes order n. So slight change to the algorithm will give you a cost optimal summation algorithm. You've said I'm going to assume a different function of n as the number of processors, and this is the algorithm. It goes in two steps. There is local computation first, then there is global computation, and at the end of it, you've got the sum. Okay?
No, but if you see it, so some of the processors were idle for some time.
Yes. But still, few enough processors were idle for few enough steps that they don't matter at the end, right? They don't go into the cost. And so there is a lesson here. It says that if you can somehow break your task into doing some independent things first, right? Reasonably large parts can be done in a sequential way. independent of other processors' relatively large parts, then you're likely to gain. As long as your large part is not so large that it takes up all of the computation and every other processor is idle. As long as, and there you can break it into a chunk size that is big enough to do significant amount of work completely locally, sequentially, and is small enough so that there are enough of them to keep many processors busy, you're going to get a faster algorithm. Okay? And so that brings us to the notions of optimality. So work optimal is something that takes amount of work that is equal to the best sequential algorithm. Okay? Work optimal doesn't mean it's going to be the fastest for every machine. Right? Because on some machines, the number of steps becomes important. If I've got a big enough machine, if I had said, I assume n over log n processors, and you give me n over log n processors, then why do I need to care for cost or work? Just the steps is how much work it's going to, how much time it's going to take. Because I have no need for subdividing work among p processors at each step. And so this is another way of looking at the same thing. If the time, so work optimal parallel algorithm takes time order of t prime n, right, which is the same as t prime n is the time taken by the best sequential algorithm you can come up with. So work done by the work optimal parallel algorithm is the same, t prime n, big O of t prime n. If you schedule it on p processors, now if you only have p processors, then t sub p of n is the same as before, right? There's nothing new here. T prime n over p plus t over n. And how will you get the best speed up? You know the time you are taking, which is t sub p of n. You know the time that the best sequential algorithm would have taken, which is t prime of n. Right? Your time, or rather their time divided by your time, is the speed up. And optimal speed up would be p. If I have p processors, I would like to go p times faster than the sequential algorithm. And so I'm going to relate that to p. Right? The speed up, which is in the square brackets over there, which is the ratio of the two different times, should be theta of p. And in order for that ratio to be of theta of p, you can do a little bit of math. P is going to be the ratio, again big O, of the ratio of the time taken by the best sequential algorithm divided by the time that you are expecting your parallel algorithm to take. It's the same thing as before, but it says that P is big O of that, right? As long as P is, you don't have more processors than that, you've got an optimal, also cost optimal solution. It is work time optimal, that is, it is work optimal as well as time optimal if you cannot now improve T of n. T of n is the time you would take in your parallel algorithm. Okay?
So with addition you could identify things which you, I mean, is it always possible to do what we did to addition to any algorithm and make it cost optimal?
So that Brent's theorem applies to anything. It is possible to do that to anything. And so there exists a range of processor values for which a given algorithm is really good. And beyond that, if you have more processors than that, that algorithm is not the best. Right? For example, again coming back to the summation example, if I break it into two parts, that's only good as long as P is no more than n over log n. It can be less, actually. Just work it out. If you had n over log squared n processors, it will still be okay. But if you have enough processors, if you have a large number of processors, then a different algorithm may be better. One that keeps those as many processors as you might have busy. Okay, so again, I've said this before also. So work optimality is the main thing we'll be focusing on though. If we can come up with something that is work optimal, we can worry about making the time better if we can. You will generally not be able to get, so if I have summation which can be done in order n time with a large enough processors p, I would like it to be done in n over p time, right? So if I have n over n log n processors, then I know it takes log n time. But if I had n processors, then I would like it to be done in one time, unit time, and that wouldn't be possible. Okay, and we'll look at the complexity classes that say what or define complexity classes in the parallel context.
What is T star and
T star.
GPU goes to T star. P equal to order of T star and.
Oh, there is a typo there. There should have been T prime. Okay, there's no T star. Let me fix it before. All right. So we've talked enough about PRAM. In summary, in short, it is just a computation model which helps you argue about things, reason about things. It's something that makes it easy to design and specify your algorithm. Not just that, because it has been popular, there are lots of algorithms available for it. So you can use them as subroutine into your overall algorithm much more easily. It is also not exactly what hardware does, right? It doesn't have the constant time shared memory access. And it's worse than RAM, right? RAM also doesn't have constant time main memory access. And the differential between RAM's predicted performance and actual performance you observe in practice when you actually run things can be sometimes large, but here it can be even bigger. And because keeping that keeping the impression that shared memory access is going to take the same amount of time going is a bit harder. So in any case, people have looked at various other kinds of computation, models of computation for parallel computation. And we're not actually going to talk about most of them, because at some level they have some correspondence with PRAM. Okay, there may be a log factor for any given algorithm. You assume PRAM and you assume something else because they can be simulated with respect to each other in log n time, or each step of some other model can be simulated in log n time by PRAM. You're going to get a cost that is log n times that other models cost. Okay, so the differential is not going to be that significant. But we will discuss one thing which is often called the bridging model of parallel computation. Okay, which was originally designed to kind of parallel the von Neumann architecture. Right, von Neumann architecture is a bit more concrete than RAM, the RAM model of computation. It still is not a real computer, but over time it has come to represent pretty much every sequential real computer, which says that there is a processor, there is a memory, there's some I/O stuff, there is a control path, and what happened to all my control paths? Okay, and programs are stored in the memory. You take out a program, you execute an instruction of the program, which is done again by sending some information into the registers of the CPU and all that. And RAM model is just one level of abstraction over it. And because this von Neumann model is a pretty good representation of a real computer, it's kind of a bridging model, right? Now, if you see that PRAM is not actually helping out in predicting performance, you can get to the von Neumann model. Right? In this case, there's also a richer version of von Neumann model where memory is hierarchical, you caches. And so the attempt to do that in the parallel context is this thing called bulk synchronous parallel model of computation.
Can you repeat previous slide again? Means what is the use of studies?
Use of what?
Studying this model.
Okay, now I've got to do this again. Von Neumann is essentially, it's something that sits between a more abstract RAM model and a more real computer. Okay, so one is that it helps the computer designers restrict their design space. So they keep their designs similar to the von Neumann model. The other is that if the RAM model is not predicting your performance, you can get down to what von Neumann model would have done. You go to one level deeper because you know that it's leading you towards the real hardware, more components of the real hardware. And so the role of von Neumann model was expected to be played by this BSP model. Okay, but over time it has also become a model of computation, a model of parallel computation, which takes away that idea that all shared memory accesses can be serviced in a constant amount of time. And the idea is that you've got a virtual set of processors. Okay, again, you can assume as many as you like, and each processor has some local memory, and there is a network. Instead of a shared memory, there's a network that lets you communicate something to another processor. Okay. Again, the distance from processor to processor is not explicitly modeled here. Right? So it says that if you are sending m units of data to any other processor, it's going to take whatever your network speed times m is. And so there are other variants where even that distance is taken into account, but we'll leave it at this, where there's a point-to-point interconnect, and there is this notion of a super step, which is very similar to PRAM. In the super step, you do some local computation, okay? You do some communication, and then there is a barrier synchronization at the end. Okay, and once everybody reaches that barrier, they start the next super step. And so it kind of looks like this. You've got a bunch of processors running. At some time during their run, they can do some communication with other processors, which means you send something to the network, put an address to your packet, and the network will deliver it at some point, you don't know when, to a destination processor. Okay. You may not assume that that guy has received something at any given time. Okay. Or a receiver may not assume that I can start to use it because that value has been updated in my local memory. And that's where this barrier comes in. After some amount of computation, local computation, they say, I'm done with my local computation, I'm done with mine, I'm done with mine. Everybody says that. And then they're going to be synchronized by the underlying computation model by a barrier. And before they proceed from this barrier, all the messages have to be delivered. So in the next super step, they're going to have, they can assume that the data has been delivered or the data has been received. So it just collects that data. It's just different pieces of data. So there's no notion of clashes. The number of the super step size is said to be L, and so there are multiple ways in which you can figure out how expensive a given algorithm is. you can simply count the number of super steps. So you design your algorithm in terms of super steps. There is facility that you may decide that you're not done with your super step yet. So all the processors are doing something, and they have determined that L is the step size, it's a fixed number, and after L somebody says, oh, I'm not done yet. Then somehow the global state is accessible to everybody, and everybody knows that the super step didn't get done, and the next L time units, they're on the same super step. So those people who had got done have to remain inactive. Okay, so then you simply count the number of super steps that were taken. More detailed accounting that is subsequently done. We'll talk about that also. But essentially, the idea is that it's going to be similar to PRAM in that it's simple to argue things in, simple to design for, and the cost that you're going to ultimately come up with will be a little bit more reflective, because you're going to ultimately account for the number of messages you're sending. Okay. It still doesn't talk about the distance. It doesn't talk about the details of how many messages you're sending, right? It says that you're sending some number of messages of some fixed length. Okay. So then the count of the messages is all that's accounted for. If you say that I have, and you can simulate, you say, suppose I had to send messages of different sizes, then it says, fine, you can send k messages of 1 unit or 1 message of k units. The same thing to me. Okay? Or k over 2 messages of 2 units each. So you simply figure out how many 1 units you've got, and that's the accounting. And that's not always the truth, because there is latency, notion of latency involved, right? You say, I'm going to send a message that's this much. You start sending. There is some overhead to the beginning of the send, and then the messages get delivered quite fast, typically. So there is a fixed overhead. So if you have lots of small messages, it will take usually longer than 1 large message. So those kinds of details are not accounted. So more detailed accounting is with this notion of H relation. And it says that there are H messages being sent in a super step. And the network has certain speed. It has some throughput. It can deliver G messages per unit time. Okay? And you figure out how many messages, how long it will take to deliver H messages. Okay? And you figure out how much time each computation is going to take. And you figure out how much time barrier is going to take. Okay? And so here you're seeing just the communication part. We'll look at the other aspects of the accounting. In the communication part, it basically says, in short, there is one scale parameter that relates it to how fast computation is versus how fast the network throughput is. And that value is G. So if you're sending H messages in a super step, then your cost is H times G. G is constant for the machine. H is what the algorithm provides. Okay. It argues that I am accounting for the overhead, the startup cost, because typically startup cost is going to be much smaller than GH, and hence I can subsume it into GH. And so GH is a good enough indicator of how long it will take on a real machine. And again, as I said, it ignores how many messages, what size the messages were, who you were sending the messages to. All of that is not part of the accounting.
If I said more than H,
H is the parameter that the algorithm generates, right? So if you are sending H messages, then the cost is H times G. We have reached the end of time. There's a little bit of accounting of this left. We're going to continue that on Thursday. Before moving on to more practical techniques, how you use PRAM to solve some of the common problems, as well as some more higher level programming decomposition techniques. How do you take a program and make it parallel? Figure out how to turn it into a parallel program. Okay, so we'll stop here. Any questions?
So the tester program that you have picked,
The idea is to figure out how it's going to call you.
no, can you put up a program which also checks for the sorting and the return keyword and the time, account for the time that you took and whatever parameters you're going to mention?
We'll do that shortly. Understand what the model is, understand what the cost model is. Right, so this, I'll revise this slide, which essentially says that there are some number of processor memory pairs, right? We call them virtual processors or workers or whatever. And then there is a network. That network is how processors communicate with each other, but the communication is point to point. So a processor says, I want to send this data to that other processor. All right?
So what is virtual processor?
Virtual processor it means that these are, as in the context of PRAM, right? There were any number of processors that you wanted. So in the same sense here also, there's any number of processors that you want, which can be implemented with P processors. Okay, so in the context of the model, you don't even have to think of it as a virtual processor. It's a processor memory pair and a network, right? Any number of processor memory pairs and a network. And you do your local computation, and that is not in lockstep. But after a certain period of time, you're going to synchronize with every other processor. Okay, so there is a barrier which says that all the processors have done with their local computation step. Okay. If they are all done with their local computation step, that also means that they are done with all the communication that they were doing during the local step. Okay. There are variants in the model. There is a variant where it says you do local step, then you do the communication, then you wait for the barrier. There's no theoretical difference between that versus when you overlap communication with your computation and then wait for the barrier. And the implicit assumption is that only after you've come out of the barrier can you assume that any of the communication that you did before the barrier has been completed. Okay, so the data that you sent has either been received or basically that the data that you sent has been received, or the data that you're waiting to receive is here. Somebody must have sent it. Okay. And for the cost model, which is where the intent of this model was to make the cost accounting a little bit more precise, breaks things down in terms of how much local computation you do, how much time is being spent in communication of the data, and how much time is spent on making sure that everybody comes to the same synchronization point. Okay, so there are three components of the cost, and those are listed here. There is a fixed cost associated with the barrier, given the number of processors, right? So more processors means there may be more of a fixed cost, but once you have determined how many processors you have, cost becomes fixed. So there is a fixed cost for barrier, and then there is local computation step, however number of steps that the largest of the computation takes, because everybody need not do the same amount of computation between barriers, right? So that's the super step. And communication. And communication is based, just purely on the number of messages that are being sent. Okay, so there are H messages being sent in one super step, and G is the throughput of the network, then H times G is the cost of those messages. So throughput is essentially a relation. Don't think of it in terms of bytes per second, the standard measure of throughput. It says how many units of network delay or network time is related to 1 unit of processor time, right? So that you can add them together. When you say I am taking W units of processor time, I can't simply say I'm taking H units of message time. G relates how much the processor time and message time, the ratio of processor time versus message time, right? So you bring everything into processor, for example, you bring everything into, in this context, everything into processor clock, so to speak. So G is the multiplier between the message clock or the network clock and the processor clock. And then there is a fixed amount L for the barrier, which is again given in terms of processor clock. So you add all of this together and you've got the total amount per super step. And you add it across all the super steps and you've got the cost. How long a given algorithm on this model is going to take. Okay. And this is where the non-overlap model simply adds up W plus HG plus L. In an overlap model, you will say that some W may overlap with some HG, so it may say max of WI plus max of HIG, and then you add those together. And so there are variants of it, but at an asymptotic level, that's not going to make much difference. So now let's step back and compare this to PRAM. What is the benefit of this model, do you think? Or is it really more powerful than PRAM?
So one question, do these models require specialized hardware? Like BSP is specialized hardware for implementing algorithms that are models?
Not necessarily. Not necessarily.
But here you are assuming that you have this interconnect, point-to-point interconnect.
Well, it just means that you need to be able to send message from point A to point B, right? You can do it on internet. As long as there is a network which connects every pair through whatever the topology of the network may be, and as long as there is local computation capacity, right? And here it doesn't say that local computation is essentially a RAM. The amount of local memory is unlimited. That won't exactly be true, but at least at the level of the computation model, we never say that we have run out of memory. Okay.
This is explicitly taking into account the communication cost, which we did not in the RAM.
This is basically taking the communication cost, right? In the RAM model, we said it's every step. So at a high level, there is a lot of differences. In RAM model, every step was synchronous. Here, there are a big set of steps, which then causes some barrier to be encountered, after which again a big set of steps happens. If you think about it, PRAM model can also be thought of at the same way, right? That big set of steps is one step. Because everybody is waiting for the barrier, it's like they have to spend that time for that step. So the barrier becomes that sync point. So instead of each local computation being what in the context of PRAM it used to be, read something from the shared memory, do some local computation, write something to the shared memory. It has become do some local computation, decide what you want to read and write to the shared memory, do that, and then start the next step. Okay? So at that level, it still remains synchronous, right? It's basically lockstep. The step has been expanded into here is communication, here is local computation, here is some barrier. And so hopefully it's a little bit more realistic, but capacity wise it's not really adding that much to PRAM. And in other words, whatever you might be able to do on this model, you can simulate on PRAM. Okay. There is another model which is again going in the same direction further. Just like in PRAM we said there are asynchronous versions of PRAM. Here also there are asynchronous versions of BSP. And the one that is the most commonly used, mostly in theoretical context, right? So this is not something that lots of people implement as a programming model interface. Right? PRAM, again, is not something necessarily that is implemented as a programming interface directly. Okay, so these are models where you can specify an algorithm, reason about it, but then you have to see how it relates to an actual programming interface, an API, like an OpenMP interface. Okay.
So, so we are saying that BSP is equivalently powerful to PRAM.
Right, but the cost may be different. The number of messages you sent, there you can say that one step took 1 unit of cost. Here you say one step takes some constant. Is it some constant or is it some constant plus h? Right, so if that h is dependent on the number of the size of the input, then the cost will be starkly different. And there you said in one constant unit of time I was able to get this data across. Here you say I take log n time to send this data across. So that log n will appear in the cost. So the cost will be different, but what you could have been able to do, you would still be able to do.
Cost will be typically more, specifically, not just different.
It need not be more, right? If everybody is sending constant amount of messages, right? If every processor sends one message every super step, then it's the same cost.
Basically, you want to have a common platform of arguing the performance of two algorithms, right? No, so that is one aspect of it. The other is being able to even describe the algorithm. And so this is the LogP model, which is the asynchronous version of the BSP model, where you don't necessarily say everybody is coming to a barrier. There is pairwise synchronization. I and that processor are going to somehow come to a conclusion that we have shared our data. Okay? And this is not very dissimilar from MPI that you will shortly get to, where we basically say, I send you something, you receive something, and there is some handshake that happens that I know you have received it. Okay? Until you receive it, I'm not doing anything else. I'm waiting there. It's like a barrier. I get past the send call when you get past the receive call. Okay? And here also for the cost accounting, there is a latency added, which is a minor change from the earlier case. You simply said that there is so many units of time spent in sending a message, okay, of unit length. Here you say that in sending a message, the time spent is some fixed latency, because latency is the time that he will receive, the receiver will receive the message after I have sent it. So some general throughput level which says I can send G messages per processor clock time doesn't help you. Okay. So the size of the message becomes important.
In model here also there is some master.
No, there's no necessary notion of master node. Those are implementation issues. And there can be a variant of MPI where you don't need master node. That's just the way it is implemented. And in here, there is no notion of master node. They're all equal. The only thing that has really changed is that we don't come to the barrier together. I negotiate my synchronization with every other processor individually. Okay.
Why is it called LogP?
It is called LogP because of the things it uses in the computation. So L is for latency. O, so it has nothing to do with log. O is some symbol that they used for, I think, the local computation time. G was the network, and P was something else. So it's just an acronym for what the cost model. Any other question? Okay, so there are many more, and then we can do a whole course on that, which I don't intend to do. What I will do though is relate. So when you read RAM, you also read about complexity theory. You understand what asymptotic behavior means, whether some problem is inherently hard. Can you make a fast solution for something? So we'll also get some flavor of that for the parallel context before moving on to some more practical things. So there is this class called NC. Okay, it's an acronym, again, Nick's class. Okay, so Nick Peppinger was the name of the author of the paper who proposed this first, and so it started to become known as Nick's class. And it says that Nick's class is the class of problems where, using a polynomial number of processors, you can solve the problem in parallel in polylog time. Okay, so log raised to some constant n. Right? So it says log to k1 n time is what you will take if you have n raised to the k2 processors, right? Where k1 and k2 are it's constant, but a good parallelizable program will have those as small constants. So the class NC is the class of algorithms that have a polylog time parallel solution if you give a polynomial number of processors. Okay. How do you think this would relate to P? P is the polynomial in PRAM model. Anything that will take polynomial time.
In one processor, it will be understood by k2 into log k1.
Sequentially it will go.
If you compute everything sequentially, so understood by k2 into log is polynomial.
It's still polynomial, right? So anything that is NC is definitely in P. Because it can, if you took that problem and solved it sequentially, you can do it in polynomial time, total polynomial time. Okay. Okay, is everything in P in NC? It is an open question. Just like we still don't know whether P is equal to NP, we don't know whether P is equal to NC either. Okay. And there is a talk on just that topic next week, which discusses some recent developments. All right, so the idea is that if you do it in parallel, you should be able to do it in faster than polynomial time. Okay. Is work going to be an issue for NC algorithms? Before I get to that, so I think I already said this, but it's worth repeating. NC algorithm basically says that it's a parallelizable algorithm, right? It's not an inherently sequential algorithm or problem. If a problem is inherently sequential, that means you can use as many processors as you like. You're going to not get great speed-ups on it.
But we have not found such a problem.
You have not found such a problem?
Otherwise, this might be such.
No, the problem may be there. We may not have found the solution. So as of now, the state of the art is that you cannot find an efficient parallel solution for it. We don't know that there doesn't exist one. Okay? So if it doesn't belong, if you cannot prove that it is an NC, that means it is, for the time being, inherently sequential. And this brings us to the question which some of you are probably thinking of right now. Is binary search, first of all, is binary search NC? Even one processor can do it in log n time, right? So it is definitely NC. Is it inherently sequential? Meaning, can you get reasonable speed up from the parallelization? And the answer is, in this case, no. And so that basically shows a limitation of this definition.
Is that no or can't say?
Answer is pretty much no.
Because we know the algorithm. It's not like we don't.
Yeah, we are talking about binary search algorithm, not search in general. The definition.
Binary search algorithm and you want to parallelize? I mean, you're essentially going to change the algorithm.
You will. Let's get to that discussion. We will shortly. The question. What was the question I asked earlier?
Is binary search parallelized?
No. We already went through that. Yeah, the question I asked was, or rather the answer I was given was that NC model is not necessarily an overarching definition that says if it is an NC, it's good in terms of being parallel. It is not in NC, then it is not good. Not in NC probably means not good, but just because it's NC doesn't mean it's well parallelizable, because binary search already happens to be a log problem. And so this definition that says that I can find polylog solution will only work if you cannot find sublinear solutions in the sequential world. Okay, let me stop here.